So here we'll continue with the example of regression analysis using cross-section data that we started in the previous video. And in this video I'm going to concentrate on how we can test for heteroscedasticity and then how to deal with that. So first thing I'm going to do is to rerun the code from the previous video, which imports the data and estimates the basic model. So all I need to do here is to highlight the code that I ran and then simply run it. And this of course illustrates the advantage of using a code-driven package like R rather than menu-driven, because once you've written the code you can easily rerun it. So rather than pressing Command Enter here, I'm going to click the Run icon here, the Run button, which will run either the current line or the selections in this case. So instantly we get a rerun of all the code that I did yesterday with the results, and the plots are here too. Now the example that I'm using from Green here is actually in the chapter on heteroscedasticity, and so not surprisingly this equation here, this model does exhibit heteroscedasticity as a problem. We can confirm that by running some tests. Now the first thing that Green does is to look at this informally by plotting a graph of the residuals against the income variable. So let me do that here. Now this in fact reproduces figure 11.1 in Green. It's on page 216, and it definitely seems to show that the variance of the residuals increases, that it's non-constant and increases with the level of income. As Green points out in the chapter, it's often the case that in models involving expenditure regressed against income, that the variance of expenditure does vary with the level of income, and that's what we're finding here. So that's just a quick informal test. Now let's run some of the formal tests for heteroscedasticity. Before I do that, I'm just going to clear the console here by pressing, of course, Control L. Okay, so the first test is the Goldfeld quant test, which is run with the GQTest function, which is in the package lmtest. So making sure that lmtest is loaded into memory, which it is because I ran this line, of course, previously. Then we can run the command. Now you need to specify the model, the variable containing the model results, the lm object, regg1. You can then also specify how to order the data using the order by option, and it's usual to order the data by the variable which you think is linked to the heteroscedasticity. And then you must also specify the data frame using the data option. There are other options you could use. Again, as always, if you want to know more details about the various arguments, simply look at the help system. So if I put my cursor here on the, you'll see the options here, but if you want more information, cursor on the formula, press the F1 function key, and that of course brings up the help for this function, which as you can see is in the lmtest package. So basically you must of course specify the lm object. The others have have default values which you can leave, but normally you want to use the order by one. So running this, we get a Goldfield quant tested to 15.001, which is the same as in Green, and of course the null hypothesis here is homoscedasticity, and that of course is rejected. Now the other main test which Green runs is the Brauch-Pagan test, which again is a very common test of heteroscedasticity. That it uses the BP test function, again in lmtest. So if I show the help system for that, again you can see the various options. Apart from specifying the lm object, the others have and the data one. The others have default options which you can leave. If now here I'm specifying that the explanatory variables which are affecting the variance are income and its square. If you don't specify both formula, then as it says here, it will use all the explanatory variables in your model. Now the other option I'm specifying here is student eyes equals false. You have to set that if you want to get the original Brauch-Pagan test statistic. If you don't specify that, you'll get the student eyes one, the Koenke-Bassett one, which I'll come to next. But running this one here with student eyes equals false, I get a test statistic 41.92, and again you'll see, if you look in green, you'll see that's the same value that he gets. And again, the null hypothesis here is rejected. Now green also does run the Koenke-Bassett version, which is meant to be better if there's a suspicion of normality in the residuals, of non-normality in the residuals, I should say. So to run that, you simply repeat this command here, but omit the student eyes equals false option. So running that, we get 6.1869 or 6.187. Again, same as green, and again the null hypothesis is rejected here. So all of these three tests plus the graph are all suggesting that there is heteroscedasticity in the residuals and that it's related to the income variable. One problem with, as Green points out, with the Brauch-Pagan test in particular, is that it does rely on the assumption of normality of the residuals. You can run the Koenke-Bassett version, but what Green also does is to test for normality using the standard Shark-Berer test, also known as the other way around as the Berer-Shark test. That can be run using the function here, shark.berer.test, which is available in the T-series package. So if you want to run that, make sure you have T-series installed, and then of course you need to load it into memory, and then you can run it simply by putting shark.berer.test and then the variable where you store the residuals. This is one of the reasons why you want to store the residuals earlier on. So running that test here, we get 497.35. Now that's not quite the same as what Green reports, which was 482.12. I'm not quite sure of the difference, for the reason for the difference there, but it's certainly similar, and again does reject quite clearly the assumption of normality of the residuals. Okay, so given this evidence of heteroscedasticity, how do we deal with it? Well, there are usually two ways you can do this. You can either use the OLS estimates, because they are still unbiased and consistent and asymptotically normal. But of course the standard errors, the OLS standard errors are wrong, and so what you do is you replace those with ones which are heteroscedasticity consistent or robust standard errors. Now to get these, to get a heteroscedasticity consistent covariance matrix, and hence the standard errors, you use options in the sandwich package. So again, making sure that's installed, and then we can load it into memory. Okay, so the option that you use in that's in sandwich is VCOVHC, which, as you can see, clearly stands for covariance matrix, which is heteroscedasticity consistent. Now if you run that option on the LM object, on your remember this is your variable where you've stored the results of the LM estimation, it will print out a covariance matrix. There are in fact 5 versions of this consistent covariance matrix that you can access and use, which are labelled HC0 through to HC4. Now by default the vcov-hc command uses the HC3 variation. If you want something different you have to specify it. So what I'm first of all doing here is I'm finding the standard errors, the consistent, the robust standard errors here, using HC3, the default. So what I'm doing here is I'm nesting three commands here. First of all, vcov-hc, which has the option reg1, so the LM object. That of course will return a matrix, and the standard errors, or the variances rather, are on the diagonal of that matrix. So I specify diagonal here, use the diagonal function surrounding that one, so notice that's some more brackets. But of course I don't want the variances, I want the standard errors, the standard deviations, which are the square root of the variances, so I specify the square root. So I'm nesting three R functions here, as you can do so. Got to be careful to get all the brackets that are required here. If you miss out a bracket, RStudio should alert you to that. It's very good at picking up syntax errors. So running that will give me the robust standard errors here, and these are in fact the HC3 variation of this. If you want a different version, if you want, for example, the original White estimates from White's estimation, then you need to specify that you want type HC0. It's exactly the same command here, except I've added an additional argument to the vcov-hc function, type equals, in inverted commas, HC0. So that will return again the standard errors using White's original version of this robust covariance matrix. Now, if you wanted any of the others, HC1, HC2, and so on, you could of course keep repeating this statement here, this code, and replace HC0 with HC1 and so on. A quick way to do that is actually to use some simple programming. Now, I'm not going to be discussing programming here, that'll be in a later video, but basically what I'm using here is a simple for loop, which loops through these statements 5 times as I goes from 0 through to 4, and it basically runs this command here 5 times, each time using a different version, so HC0 and then HC1 and so on. Now of course the advantage again of R being a programming language is that if you write little code like this, then of course this can easily be reused. If I want to use this in another estimation procedure, all I have to do is to change reg1 there to whatever the variable is that the results are stored in. So if I run this, you'll see that I get a printout of all the standard errors using these different robust covariance matrices, HC0, which is the original White one, HC1, HC2. Now in the table 11.1 on page 221 of Green's text, he has some of these estimates of the standard errors using different robust estimators. He has the original White ones, which are these, HC0. He also has a couple of others which are labelled D and M1 and D and M2. I can't actually remember what D and M stands for. It's the name of the two econometricians who devised these alternative tests. But DM2 is in fact this one, HC2. So using HC2 you'll get the same values which Green reports here. The other DNM1, however, doesn't appear to be available via this function in R. None of the other ones seem to match his DNM2 figures. I'm not quite sure why that's the case. if you want more information about the different options here, it's HC0 is the original white ones, and HC2 is what Greig calls DNM2. Then of course simply look in the help system under this for this function here. But anyway, you can see that you can easily print out robust standard errors, heteroscedasticity consistent standard errors, using various versions of the robust matrix. They're all very similar, and they all differ somewhat from the original ones. Now we can see that if I run this command here, again I'm using this nested function to get the square roots of the variances. Now here I'm just using vcov, which is the built-in function in R for returning the various covariance matrix from an OLS regression. So I don't need to have LMTest or other sandwich loaded for this. This you can run anyway. So this will give me the same standard errors, of course, as from the original estimation. So running that, I can now compare these OLS standard errors with these robust ones, and you can see there's a noticeable difference, which of course does also indicate heteroscedasticity. Now of course, if you, given that we have heteroscedasticity, the original t-tests and the f-tests and the wall test that we did are invalid because the standard errors are incorrect. So you now want to rerun those t-tests and f-tests using some robust corrected standard errors. Now the way you can rerun the t-tests is using a function called coftest, which is again in the LMTest package. If I run this on the reg1 LM object, it will simply give me the t-values from the original estimation. So these are the original OLS results, but of course we know that these standard errors are incorrect. So what I want to do is to rerun the t-values, t-tests, using some corrected standard errors. So here I simply again use coftest with reg1, but this time I specify one of those standard robust estimators using the vcov dot equals option. Now if you just specify vcov hc, it will again use hc3 by default, which is these ones here. So running that, you'll see that we get the table again with the t-test, but this time using those hc3 errors, because you can see 229, 3.6 and so on. In fact, it gives the same results as regarding the significance of these two variables only. What about choosing HC0 or HC1? Well, again, I could rerun this command with, again, using changing, but again I'm going to use a little for loop to do that much more quickly. So I'm going to rerun this test here 5 times using the different covariance matrices. So that's, as you can see, a very nice way of doing it. I've run the same t-test with first HC0, which are White's original errors, and then HC1 and so on. And in fact, in every single case, the only two variables that are significant are income and income squared, just as in the case with of the original estimation. Now, of course, the f-test that I ran and the wall test up here are also invalid because these were run under the assumption of homoscedasticity. So we need to rerun those using these corrected standard errors. I can do that again using the wall test function again that I used before from LMTest. You can't use ANOVA, you need to use wall test. It's the same as before, except again I have to specify that I want to use some robust errors here from, in this case, HC0. Again, obviously you can use HC1, HC2 and so on. So same as before, restricted model, unrestricted. Tell it I want a chi-squared test in this case. If you don't, it will run the f-test. and then this is the important additional argument, vcov equals, and then it's vcov hc, and then similar to what we specified here, or here rather. Obviously if you want hc1, put hc1 and so on. So this will rerun the chi-squared test, the wall test, using those robust corrected errors, standard errors, and we get a value of 20.604, which again is exactly what Green reports on page 220 of his text. So this is using the white version of the corrected covariance matrix, which again, of course, as you can see, rejects the hypothesis that these two variables are jointly, the coefficients are jointly equal to 0. Okay, so that shows how we can deal with the problem of heteroscedasticity by retaining the OLS estimators but using corrected standard errors. The other option, of course, is to re-estimate the model, allowing for the heteroscedasticity. One of the common ways of doing this is to use weighted least squares. This, of course, assumes that you know which particular variable is causing the heteroscedasticity. In this case, we know that it's probably income. So I'm going to run weighted least squares here. First of all, using weights 1 divided by income, 1 over income, and then 1 over income squared. These are the two alternatives that, again, Green uses in his text. Now, to run weighted least squares is very simple. You simply use the LM function again, just as before, but you also include this additional argument, weights equals 1 over, and then you specify the variable here. So I'm going to run this again. It's the same model, of course, same data set, but now I've got weights in, storing those in reg1.wtls1, standing for weighted least squares version 1, of course. So running that, then looking at the results, we have these different estimates, of course, different standard errors. This seems to indicate that only income is significant. Now again, if you compare these with the table 11.2 in Green on page 231, you'll see they're identical, as indeed they should be. And finally, running weighted least squares using income squared here, or 1 over income squared, as the weights. Sure. So let's look at the results of that. We get this, and again you'll see these coincide exactly with the estimates reported in Green. And again, only income coming out as the significant variable here. Okay, so that shows you how to deal with, to run some specification tests, particularly for heteroscedasticity, how to get variance covariance matrices, and both standard and robust, and how to do weighted least squares.